Hey there, Seahawks, it's Miss Adams, and in this video we're going to learn about inference for the difference of two proportions. Alright, so our first example, do men and women wear seatbelts the same percent of the time? In order to find out, we take a simple random sample of 200 male drivers and another simple random sample of 250 female drivers. We find that there are 146 men that wear their seatbelts regularly and 203 women that wear them regularly. Is there a significant difference between the two sexes? What is the difference, if any? All right, so P hat M, the sample proportion for males, would be 146 out of 200, which is 73%. The sample proportion for females, P hat F, would be 203 out of 250, which is 0.812. The difference between those, male minus female, would be negative 0.082. If I was going to do a hypothesis test, my null hypothesis might be that PM equals PF. The proportion of males that wear their seatbelt regularly is equal to the proportion of females that wear their seatbelt regularly. I could also write this as a subtraction problem, so PM minus PF equals 0. All right, and the alternative could be a not equal to. All right, if we're doing a two proportion Z interval, we can create a confidence interval for the difference between two proportions. All right, our conditions for both intervals or a test, we need to double the ones for a one proportion interval or test. So we need to have two independent random samples. We need to check large counts for both N and both proportions, right? So we have N1 and N2. We have P1 and P2, right? So we need to find 4 different numbers to check the large counts. And then the 10% condition, my two different sample sizes have to be greater than 1/10 of the entire population. All right. If those conditions are met, we can use a normal model and we can do a two proportion Z interval or a two proportion Z test, depending on what we're being asked. All right, so since the normal model is being used, we need to be able to find the mean and the standard deviation, which in this case would be the standard error. So the mean would be P hat 1 minus P hat 2. This would be the mean of the sampling distribution. The standard error when we had just one proportion was the square root of P hat times 1 minus P hat over N. So for two proportions, it would be the square root of P hat 1 times 1 minus P hat 1 over N1 plus the square root of P hat 2, or plus P hat 2 times 1 minus P hat 2 over N2, all under one big square root. All right. The confidence interval formula, the basic formula is your statistic plus or minus your critical value times the standard error of your statistic. That is on the front side of your reference sheet, and then you can piece it together into the specific formula using the back side of your reference sheet. So the statistic here with two proportions would be P hat 1 minus P hat 2, plus or minus our critical value for a Z interval would be Z star, and the standard error we just talked about. So that gives us our interval. We would state our conclusion. We are blank % confident that the interval from blank to blank captures the true difference in the proportions of blank and blank. All right, so we're going to do an example of a two proportion Z interval. College students were randomly selected and asked about how much alcohol they consume on a weekly basis. Over a certain amount of alcohol consumed was considered binge drinking. Out of 5,348 males surveyed, 1,392 were identified as binge drinkers. Out of 8,471 females surveyed, 1,748 were identified as binge drinkers. What is the difference in the proportions of males and female binge drinkers? Use a 95% confidence. All right, so state, plan, do, conclude is our format we're going to use. I need to find my sample statistics, so P hat M for males and P hat F for females gives us those proportions. My confidence level is 95%. My difference in the sample proportions is 0.0539. And when I define my parameter, I'm going to go ahead and say PM minus PF is the true difference in proportions of males and females that are binge drinkers. All right, and I'm trying to pull that from the question that's being asked as much as possible. When I'm checking my conditions, random, I need to have two independent random samples. So randomly selected for both male and female was stated. The 10% condition 5,348, which is the sample size for males, is less than 1/10 of all males. 8,471 is less than 1/10 of all females. That was the sample size for females. Large counts, I'm going to do for males, n times p hat, and then n times 1 minus p hat. And then for females, I'm going to do that n times that p hat times that n times 1 minus that p hat. Gives me all values that are greater than or equal to 10. So my conditions are met, and I can do a 2 proportion Z interval. So my specific formula here would be p hat m minus p hat f plus or minus Z star times the square root of p hat m times 1 minus p hat m over nm plus p hat f plus times 1 minus p hat f over nf. When I plug numbers into this, I'm plugging in the sample proportion for males, the sample proportion for females. Z star at 95%, hopefully you're starting to memorize that, is 1.96, times the standard error. I'm plugging it in for the PM and the male sample size, and then I'm plugging it in PF, P hat F, and the female sample size. Okay. From there, I would grab my calculator and actually have the calculator run the confidence interval. So it'd be stat test. We're doing a 2 proportion Z interval. X1 would be 1392, N1 would be 5,348, X2 would be 1748, N2 would be 8,471, confidence level 0.95, and we get our interval. There we can say our conclusion. So we are 95% confident that the interval from 3.935% to 6.851% captures the true difference in proportions of male and female binge drinkers. All right. If we were going to do a 2 proportion Z test, we are comparing 2 proportions together. In our state section, we would have to have our null and alternative hypothesis. So our null hypothesis would be P1 minus P2 equals 0. Alternative would be P1 minus P2 is either less than, greater than, or not equal to 0. Okay, P1 minus P2 equals 0 is the same thing as saying P1 equals P2, meaning there is no difference. The difference equals 0. They are equal. All right, whichever way suits you best, you can use. All right, we're checking the same conditions as a confidence interval with a minor tweak for the large counts condition. All right, if our conditions are met, we're going to do a 2 proportion Z test. So because our null hypothesis was P1 equals P2, we must assume that the null hypothesis isn't true until proven otherwise. So if P1 equals P2, then we should really combine P hat 1 and P hat 2 so that we have more information about the true proportion. So this is called pooling our sample proportions together. All right, so you're only going to do this for a 2 proportion Z test. You're going to pool your sample proportions, and you're going to find P hat combined. So P hat C, where you take each X value, add them together, and divide it by each N value added together. All right, our mean, we would do P hat 1 minus P hat 2. Our standard error, we would use the pooled standard error, so I'm using P hat combined, but I'm still using those 2 separate sample sizes. Okay. My test statistic, I want to find Z is equal to P hat 1 minus P hat 2 minus P1 minus P2, which is almost always 0 because we think that they're equal, that there's no difference unless stated otherwise. And then our p-value, we find that the same way. We can either use a z-table or a calculator. In our conclusion, the same exact first sentence, so we reject or fail to reject because our p-value is less or more than our alpha value. Your second sentence is going to be we have sufficient or insufficient evidence that the percent of blank is blank, the percent of whatever. So we'll look at some examples. Back to the example from the beginning, do men and women wear seatbelts the same percent of the time? So in this example, we're going to do a hypothesis test. So is there a significant difference between the 2 sexes? Assume the conditions are met. Okay. So P hat M is 146 out of 200. P hat F is 203 out of 250. P hat combined is 0.776. My null hypothesis would be that PM, the proportion of males minus the proportion of females, equals 0. There is no difference. The alternative would be PM minus PF does not equal 0, that there is a difference. Okay, I'm not going in one direction. The question didn't lead me to do a greater than or less than test. My alpha value, 0.05, and then I need to also define my parameter. So PM minus PF is the true difference in proportions of males and females that wear seatbelts. Plan, I would check the random and 10% condition for both males and females. And then the large counts, I would use P hat combined. Okay, so I'm using P hat combined for the large counts. Then I would do a 2 proportion Z test. My formula, my specific formula is here. I will plug the numbers in. Remember, I'm using P hat combined for that standard error, so that's where I got that from. So P hat M minus P hat F is 0.73 minus 0.812 minus 0 because my null hypothesis was set equal to 0. There was no difference. The square root P hat combined is 0.776, 1 minus 0.776 over N1, which was 200 for males, and then plus 0.776 times 1 minus 0.776 over 250 for the female section. That gives us a z-score of negative 2.072. I'm going to draw my normal model. I'm going to go ahead and draw a standardized normal model that I would use for like z-scores. And I'm going to go ahead and just label my z-scores on there and be very clear to say z equals negative 2.072. And because I'm doing a not equal to test, I'm also going to do z equals positive 2.072. And then I'm going to shade both above and below those. And then I'm going to use my calculator, which I would have already used to get the z-score. But in my calculator, I'm going to go to stat, test, and I'm doing a 2 proportion z test. Plug that all in, and I get a p-value of 0.0383. All right, now we can go to our conclusion. So we reject the null hypothesis because our p-value of 0.0383 is less than our alpha value of 0.05. We have sufficient evidence that the true difference in proportions of male and females wearing seatbelts is not equal. All right, go Seahawks.